This lecture is entitled Antiderivatives and Indefinite Integration. Now, antiderivative is basically working backwards. In other words, essentially saying we have the derivative, what was the function before we took the derivative. Now, here's just some kind of notation to kind of get the idea. We'll be using that a little bit later. This function, capital F, is an antiderivative of little f on an open interval I if f prime of x equals, big F prime of x equals little f of x for all x in that I. Now, here's an example. So we're saying if f of x equals 5x to the fourth, I'm saying that big F of x would be x to the fifth, because the derivative of big F of x, right here, x to the fifth, would indeed be 5x to the fourth. So that's what I'm checking off right there, that derivative is true. Now, if you think about it, I wrote some other, I think there could be more than one possible answer for this, not just x to the fifth, because I just use these subscript notations, but couldn't the answer be x to the fifth plus 13, or x to the 5 minus 7? Wouldn't those derivatives also be 5x to the fourth? I believe they would, because the derivative of a constant we know is 0. And okay, here's where I set it right here. Now, here's a theorem we'll use. I'll get rid of that page. Okay. This says the antiderivative of f of x may be written as big F of x, the antiderivative function, plus c, where c is there to represent an arbitrary constant value, essentially any real number, like those two examples I showed you before, and where they would be the same derivative. So in this case, the actual antiderivative of 5x to the fourth is really x to the fifth plus c. And you can see that because the derivative, if c is a constant, its derivative would be 0. And and then therefore it would still be 5x to the fourth. Now here's a term, phrase, differential equations. Some of you will take an entire course on this, so obviously this isn't getting too sophisticated in this class. Cal 2 will often dabble into it a little bit further, but it's the type of material that warrants its own course. Now, oftentimes some schools will have it as, you might not think you have to take it, but they'll call it engineering math or something like that. And that usually ends up being differential equations. So a differential equation is variables x and y that involve x, y, and any derivatives of y. Yeah, so it could be several derivatives. As a course, let's see if I put one on here. No, I didn't. I'll see if I can freehand one here real quick. It would look, might not look so good here, but so I'll just go like y double prime plus y prime plus y equals, I don't know, we'll say sine of x. Okay, that looks terrible, obviously, but we're not getting into this kind of problem in this class. But what that's implying, it's a differential equation because it has variable terms that are derivatives. You're trying to find some function y where the second derivative of that function plus the first derivative of that function plus the function itself would equal sine of x. Now, I'm not even sure if that's a solvable problem or not, but I just totally made it up, but that's the idea. And so we're only looking at, so when we're finding basic antiderivatives, we're actually solving a simple differential equation. So if you're trying to solve this equation, y to the prime y prime, excuse me, equals 4x cubed, that result y would equal x to the fourth plus c. Because you can see that y prime would be the derivative of y. And then if y prime equals cosine of x, we have y equals sine of x plus c. So those are solving two very elementary differential equations. Now we're going to bring the concept of differential notation discussed in the previous chapter. Now, if you take this dy dx equals f prime of x, we're going to write this in this differential form, dy equals f prime dx. So we're going to see a lot of this, especially the dx on the right side is what's going to be the most obvious thing. Now, the process anti-differentiation is also known as integration. That's what it's more commonly called. That's a lot of syllables to have to say anti-differentiation all the time. So integration is what we'll generally be saying. And integration, symbolically, you notice how derivatives can be represented with prime or dy dx. That little curvy symbol right there, that little snake-looking thing, you put that in front of some function, that means you want to find its antiderivative. Now we have two types of and then the problems are called integrals. So integration is the process of evaluating an integral. We call this indefinite integral when it's written like this, and then when you see values here, numerical values, sometimes variables, we'll discuss that. But when you see something here, that's called a definite integral. We're starting out with indefinite integrals first. And then we'll soon, in subsequent sections, introduce the definite integral. All right. Now, okay, so in this form, the dx is there. So that's an important part of the notation. That indicates you'll see on the next page what that means. But therefore, the antiderivative, or the integral of 5x to the fourth dx, would be x to the fifth plus c. Another way you could think of this is if dy was on the other side of this. Suppose dy equaled this, like that. Or excuse me, y equals that. Y equals this. Dy equals all this right here. So your dy equals what's... So when you take the antiderivative, you're going from dy back to y. And let's see. You don't always have to have variable x. So the antiderivative, or the integral, of 4 theta cubed d theta would just equal theta to the fourth plus c. And you can see, because the derivative of theta to the fourth equals 4 theta to the cubed. Now you might be wondering, do you have to figure that out in your head every time? No, we have some rules we'll be using. We have just like we had a power rule for derivatives, we'll have a power rule for antiderivatives. I'm just picking basic examples right now that aren't too hard to figure out what the antiderivative would be without a rule. All right, so here, if your setup is written in differential form, and you essentially then integrate both sides, when you integrate dy, the antiderivative of dy is always y, and then the right side will be evaluating this f of x dx. So this dx tells you what the variable of integration is in the problem. And that's important. Let's say if we had something that had a couple of different letters in there, and we'll see that later, we would know that dx is the variable of integration. And then using that capital F notation we saw earlier, then that means the result, big F of x is the antiderivative of little f. And then, of course, your plus c, your constant of integration, which has to always be there. And here's just showing the same thing in terms of t. Now, we use the big F form, but also I'm showing you if you used, prime notation, which certainly isn't wrong, but bring that down the line here. If dy is written as g, just like so, this notation, and f of t, the antiderivative f of t is big F of t. Well, the antiderivative of something where it's already written as prime, so the antiderivative of g prime of x would just be g of x. Because if you took the derivative of little g of x, that derivative would be g prime of x. This big F notation has its uses, we'll see later, but this follows the same concept, that the antiderivative of g prime equals g of x. All right, and I'm just showing you a little kind of a mapping, sort of. It's integration's kind of the reverse process of differentiation. So when you differentiate, you're going from y to y prime. When you integrate, you're going from y prime to y. And here come some rules that we'll need. And I'm telling you that differentiation is the inverse of integration, the reverse process. So if you have an integral inside here, the integral of f of x dx, and you put a d dx out here, so if you took the antiderivative of f of x, then took the derivative of that result, you'd be right back to where you started with the f of x. That's all that's saying right there. So if you went back a step, forward a step, you're right back here. And this is mentioning that k is any real number. So the antiderivative of any constant times dx, or d, whatever the case may be, is just going to be kx plus c. So you have to be careful here because you're used to the derivative of a constant being 0, but the antiderivative of a constant is not 0. So like, for example, here, the antiderivative of 6 dx would just be 6x plus c. And then that kind of holds as a general rule that constant k times any function f of x dx will equal k times the integral of f of x dx. So you can pull constants out, but here's something that's very, very, very important in integral calculus as you advance along in your study of this material. So Stewie here looks pretty angry, and he's saying the variable of integration may never be moved outside the integral sign. So look what I have up here, how this is okay. The 4 times f of x dx, you can move the 4 to the outside, that's fine. If you have something like x, I just picked x, but it can be any variable that's your variable of integration, x squared, whatever, times f of x dx, you cannot, absolutely cannot pull that x outside the variable, the integral. You cannot do it. To solve the problem, you'll have to find some way to deal with it. Therein lies the challenge of integration. The more you learn, the more skills you develop, the more complicated it can get. You can kind of ask your average Cal 2 student for that information. Okay, so here's another one. Can't bring the x out here. But if it's a letter, see that your dx tells you your variable of integration. So any letter in this particular problem that's not x is considered a constant. So in this case, that a is representing a constant, so it is allowed, it can be moved outside the integral because it's not your variable in this problem. And okay, here's another one here. Now this property, this is a similar property to derivatives. So if you have two or more functions added or subtracted together, it's not just two, it can be more. You split it up as two pieces, like so, and you can do them individually. So that means in this example, the integral of 6x cubed plus 3x to the fifth dx you're technically allowed to split them up as two pieces, although you'll see later that you won't have to do that, but you are allowed to do that. And then just for grins, I pulled the 6 and the 3 out, so you could you can do that too if you want to, because that's the property from up here we just learned. All right. Okay, this is very important. There is no product or quotient rule for integration. You cannot take two functions multiplied together within an integral sign and split it up as two integrals multiplied together. That is completely wrong, and it's also completely wrong for division. So once again, you're going to have to find some sort of clever way to deal with it when that comes up. Now the power rule for antiderivatives, so you don't have to always do these in your head and figure out what they're going to be. X to the n will be x to the n plus 1 divided by n plus 1 plus c, but n cannot be negative 1. It can be any fraction, positive, negative, fraction, anything, but not negative 1. And you can see because negative 1 would cause 0 in the denominator. However, in a later video that I'll make, you'll see what the answer is when it is negative 1. It just can't be used. You can't. It's not from this rule, in other words. It has its own special answer. All right. So here's an example. X to the 6 dx. Now you see how I wrote it right here. Obviously it doesn't, you can have the 1 over n plus 1 to the outside, or you can put it underneath the x. That's just simple algebra. Either way is fine. So x to the 6, it would be 1 over 6 plus 1 times x to the 6 plus 1, and then our plus c. And then, so it's 1/7 x to the 7 plus c, which is the same as if you just wrote x to the 7 over 7. Those are mathematically equivalent. Now this next one's kind of interesting because this, often throws students when they're first learning this rule. You cannot apply the power rule to a variable when it's in the denominator of a fraction. Cannot do it. So to handle this one, we would have to bring it up, and there's no quotient rule, remember, so bring it up, and you just rewrite it then as x to the negative 8 dx, and then you apply the power rule. So once that's negative 8, x to the negative 8, and you see this time, I don't know why, I wrote it differently than that one, but just so you can see both ways. Obviously both are correct. And negative 8 plus 1 is negative 7 over negative 8 plus 1, which is negative 7. In my instruction, I don't have a problem with negative exponents. If it's like a handwritten type of test or something in a face-to-face class, I don't care. If you're taking an online class or taking a multiple choice exam, it may write the answers, have the answers converted back to positive. So you would probably, possibly be looking at something like this. Negative. The negative can be to the outside or wherever, but 1 over 7 x to the 7, and and I'm not going to write the plus c for this one because I'm having enough trouble as it is, but plus c follows that. So that's just the x dropping down to the bottom, which is maybe the way you would be looking for the answer in a test. All right. Just like derivatives, when we have radicals, we must convert radicals to exponent form. And then we use the appropriate power rule here. So the cube root of x squared would be x to the 2/3. I just kind of wrote that radical property. And power rule. 1 over 2/3 plus 1, and then x raised to the 2/3 plus 1. 2/3 plus 1 is 5/3, and then 1 over 5/3 will just flip over and become 3/5. Oftentimes I'll tell people that one way to think of this is once you know your new exponent, in this case it's going to be 5/3, that means the reciprocal of it will go in front. Now, of course, if we had some sort of number multiply this, and let's say if there was a 6, then it would be 6 times 3/5, but the 3/5 would still be there. So yeah, so fractions, no problem. Here's one with two functions, and so even though I didn't write them as two separate integrals, you can still take the appropriate antiderivatives individually. You know, I showed earlier that one of the properties allows you to split them up, but unnecessary. You can work with them individually without having to rewrite the integral sign twice. I just think that saves a little effort. So how about this one, 3x to the negative 5? Now, x to the negative 5 plus 1 is negative 4. So I guess I kind of skipped a step here, but that would have been 1 over negative 4, which is the same thing as negative 1/4. And you see we have a 3 here. So it's 3 times that negative 1 over 4. So there's our negative 3/4 x to the negative 4. And for this one, negative 3/4 plus 1 will be 1/4, which makes this be 4 over 1, which of course is 4. 4 over 1 right here, but you have a 5 right in front, so 5 times 4 is 20. And negative 3/4 x to the negative 4 minus 20x to the 1/4, and then our beloved plus c that must be there at the end. Let's look at some trig antiderivatives that you will need to know. Well, if you know the trig derivatives, then the antiderivatives won't be too bad, but it's a little confusing at first, just like sometimes anything new can be a little confusing. This is what I find from when I'm working with students in a face-to-face class. They got to get used to, you know the derivative of sine is cosine, but see, the antiderivative of cosine is sine. Now, because if you're not sure, you think about it. Well, it's because the derivative of sine is cosine. It's tempting to think the antiderivative of cosine might be negative sine because of this, but that is not true because we're going the other way. Now, what happens with this one is we're just taking the antiderivative of sine without the negative. So obviously the negative has to go somewhere. So it's like multiplying both sides by negative 1. So the negative comes over here. So therefore the sine of x would be negative cos of x plus c, which you could also check quickly by derivative, because the derivative of cosine is negative sine, so it needs this extra negative in front, so therefore negative of negative makes positive. So there's how you can look at it. Okay, so I'm not going to read all of these out. I'll do one more real quick. The derivative of tangent is secant squared, therefore the antiderivative of secant squared would be tangent. See, it's just reverse. And they did the same thing with these last two. They moved the negatives over to the other side and dealt with it that way. All right, so it's a good idea to know those. Let's look at some more examples. This one's pretty easy. And there's 3 terms here, but once again, I did not have to write 3 integrals, but I am finding 3 antiderivatives without putting the symbol 3 times. So 8x cubed would be 8x. 3 plus 1 is 4. X to the 4th over 4. And then we have minus 9x cubed over 3. And then plus 4x. And then that simplifies. 8 over 4 is 2. They may or may not simplify. That's not a rule or anything. 9 divided by 3 is 3. 4x, and then your plus c at the end. And there we have it. Now here's one with a radical. So the square root of x is x to the 1/2. Now this one, notice some people get confused and they bring the 2 up. The 2 doesn't go anywhere. The 2 stays right there, only the radical. So it's 1/2 still right here, but the x comes to the top and becomes x to the negative 1/2. So 1/2 plus 1 would be 3/2, which that little trick I was showing earlier. So I kind of skipped a step here, but instead of writing 1 over 3/2, I just flipped the exponent. So that puts a 2/3 right there, which is, 1 over 3/2. Same thing, negative 1/2 plus 1 is 1/2. So that makes a 2 here, because 2 is the reciprocal of 1/2, but then we have a 1/2 already in the problem from right here, so we have to deal with that. So the 1/2 cancels the 2. And there we have this answer, and with our plus c at the end. All right, here's one with division. So as I mentioned before, that there's no quotient rule here. So the way you would handle this kind of problem is you just divide it term by term. So you just put x to the 4 over x to the 4 minus 3x squared over x to the 4 plus 5 over x to the 4. So x to the 4 over x to the 4 is 1. And then 3x squared over x to the 4th. I just went ahead and brought these up because, you know, you might as well get the exponent to the top. You can always drop it back down again in your answer. But x to the subtract 2 minus 4 would be negative 2. And then x to the 4 just comes up and becomes negative 4. So the antiderivative of 1 is always x. In other words, antiderivative of any constant would just be that constant times x. So obviously I didn't need to write 1x there, but it is. So it's that. And of course the derivative of x is 1, right? So power rule, 3x to the negative 2 plus 1 is negative 1 over negative 1. And then negative 4 plus 1 is negative 3 over negative 3. And I just kind of tidied this up a little bit. So the negative 1 would cancel that negative and make positive. And then there's a negative 3 on bottom, so I just brought the negative out here. Got rid of that plus sign. So I have 5/3 x to the negative 3. You know, on a handwritten question, I would consider that perfectly acceptable. But, you know, keep in mind, if it's multiple choice, whether it be a quiz or an exam, you may have to drop those down to the bottom. And it would look like this answer. I did this in Maple. And it dropped the x, it dropped the x cubed. It's kind of weird, but Maple, they didn't write any programming Maple to put plus c at the end of it. I guess they just assumed the user would know that and not worry about making it come out in the answer every time. But there's absolutely supposed to be a plus c there. There we go. So, like I said, they probably just figured we'd know that, so. Some more examples. Let's see. New variable, theta. Antiderivative of theta squared would be theta, the 2 plus 1 is 3, divided by 3. Antiderivative of sec squared, we saw a little while ago, is tangent, and then plus c, and that's it for that one. Next one's a little tricky. It's two things multiplied together, which there's no product rule, but you can certainly, because of the parentheses here is to the first power, well, we wouldn't mess with a problem like this if it wasn't the first power, but you distribute, well, until later on when we learn the integration by substitution. So I distributed. Sec times tan is sec tan. Sec times sec is sec squared. And this was on that list of trig antiderivatives. I didn't read this one out, but it was on that page back up there. But the antiderivative of secant y tan y would be sec y, because the derivative of sec y is sec tan. And the antiderivative of sec squared would be tan, so the negative comes down. So the final answer would be sec y minus tan y plus c. How about this one? Sine over 1 minus sine squared. All right, looks kind of interesting. Now, this is where, you know, trig identity would be helpful. That's on that trig sheet. 1 minus sine squared is cosquared. Now, later on, we'll see another video where it shows another way to do this problem. But for now, we have to do it the way I've done right here, because it's the only based on the knowledge we have at this point. So to solve it from here, you have to split the two cosines up, which leaves you sine over cosine times 1 over cosine. So sine over cosine is tangent. 1 divided by cosine is secant. So now we have tangent times secant, which the antiderivative of tangent times secant would just be secant. All right. Initial conditions and particular solutions. All right, that's kind of some differential equation terminology, but that's all right. It's not going to be that bad. Now, when you're solving these problems, technically when you have these problems with the plus c, those have a name called the general solution. And so you have the plus we call it the general solution when you have the plus c. Now, a particular solution is where the problem gives you some extra information, and that enables us to determine a value for c. Hence, it's called particular solution because it only works under a particular instance. So let's say that we're given a function where we're given the derivative, and then they give us some other information such that when x is 2, y has to equal 7, f of 2 equals 7. Well, for that to be true, you certainly couldn't have a c in the answer. We would need a number for the c to be able to make it equal that 7. That's what we'll solve for. So it's not that bad. So you'll put in 2 for the x, and you'll put 7 on the other side, and then you'll solve for the c that makes it fit. All right, so it's not too bad at all. Now, I copied this one out of the book. I don't really like using variable s, even though I wrote it that way. It looks like I copied it from the book, and they had s. I try to avoid it. S, looks, trying to write this in class, it looks too much like a 5. But I try to really make my s's curly enough and make a distinction between what 5 and s are there. All right, so we have 10s, not 105, minus 12s cubed. So it's essentially 10s to the first. So that'll be 10s to the 1 plus 1 over 1 plus 1, minus 12s to the 3 plus 1 over 3 plus 1. So 10 over 2 would be 5, and that makes that s squared. 12 over 4 is 3. 3 plus 1 is 4. And then plus c. So it's 5s squared minus 3s to the fourth plus c. Now we have to come up with the value of c that satisfies this condition here where f of 3 equals 2. So like I said, we'll put 2 over on the left side because that's the result right here. 2 is the result when the s will be 3. So put 3, put 3. So just kind of get your calculator out and figure all this out. I didn't show all the arithmetic here, but I'm sure you won't have any problem with that using a calculator. But I got c to be 200 to make this equation be true. Therefore, our particular solution now for f of s would be f of s equals 5s squared minus 3s fourth plus 200. So that means that this problem satisfied two conditions. Its derivative would be 10s minus 12s cubed, and then f of 3 would equal 2. So it satisfies that extra condition. Here's one where you can actually work it back 2 steps. You can start with the second derivative. So therefore, technically, you think just like you go forward with the derivatives, reverse is the same. The first derivative is the antiderivative of the second derivative. So I take the antiderivative of 8x cubed, and I didn't. Okay, you should probably get used. Yep, so it would be 3 plus 1 over 3 plus 1 is 4. 8 over 4 is 2. 2x to the fourth. At this point, even if I don't have the work shown here, I'm certain you'll be able to figure it out. And so it's 2x to the fourth. Now I used a C1 here. It's okay if you use C because we're going to have another C coming up. So I'm using C1 and C2 just to make a distinction. So we're looking for a function whose second derivative is 8x cubed. F prime of 2 needs to equal 10, and f of negative 1 would equal 7. So if f prime of 2 equals 10, I'll put 10 right here for f of prime of x on the left. I put 2 in for the x. So 2 times 2 to the 4th equals 10, and I got negative 22 for C1. So that means f prime of x is actually 2x to the 4th minus 22. Now we have to integrate this one more time. So f of x then will be the antiderivative of f prime of x. So now we've reduced it one step to where the next rest of the process is just like the last example. So the antiderivative, x to the 4 plus 1 over 4 plus 1, so that makes it 5 on the bottom, x to the 5th, so it's 2/5 x to the 5th minus 22x plus c2. So what is this information telling us? F of negative 1 equals 7. So you put 7 on the left side, negative 1 on the right, put negative 1 for x, negative 1 for x. And so it's kind of got a fraction here because of that 2/5, but you can work it out in the calculator. You'll get negative 73 over 5. So there's your solution that satisfies all those conditions. 2/5 x to the 5th minus 22x minus 73 over 5. So you notice, so these kind of problems do not have plus c at the end. So the particular solution one's no plus c. Okay, these are just some maple commands. Don't worry too much about that. And I kind of did a little research to figure out how to do this. Put blah, 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 blah. And it matches my answer. So that's good. All right, here's one with the trig function and the second derivative. We have f double prime of x equals sine, f prime of 0 equals 1, f of 0 equals 6. So f prime will be the antiderivative of f double prime. So the antiderivative of sine of x is negative cos of x plus c, and I use c1 here. So if f prime of 0 equals 1, put 0 in there for x. So keep in mind that, cosine of 0 is not 0. So cosine of 0 is 1. So basically you have negative 1, then you add 1 to both sides. So it makes it 2. So that means that's the result for f prime. So now to get to f, we integrate negative cos of x plus 2, which will equal the antiderivative of negative cosine will be negative sine. And the negative's there just because so in other words, antiderivative of cosine is sine, but then the negative is in front, so the negative just carries over. The antiderivative of 2 is 2x. And I just put an arbitrary c2 there. So we know that f of 0 equals 6, so I'll put 6 on the left side. Sine of 0, 2, 0 plus c2. Now cosine of 0 equals 1, but sine of 0 is 0. So we get a couple of zeros here, so therefore C2 would have to equal 6. Therefore, our particular solutions, f of x equals negative sine of x plus 2x plus 6. And that concludes this video lecture.